Welcome back, everybody. This is part 2 in the series on building a single-ended tube amplifier. And if you'll remember, in part 1 we covered kind of the overall architecture. We selected a single-ended amplifier architecture and went through various tube types, and we ultimately ended up selecting the 807 tube type. Today what I'm hoping to cover is kind of the overall amplifier design, what the schematic looks like there. Get into the components and the build of materials, and we'll probably call it a wrap for episode 2 here today. Okay, so when you're designing an amplifier, the first thing you need to realize is that you're designing it around your tubes. First and foremost, more than any other components. Almost every resistor in an amplifier, every capacitor in an amplifier, the chokes, etc., they're all designed to be setting up the parameters around this tube properly so that it operates in what I'll call its happy zone. Its typical operating zone. And so the manufacturer of tubes actually produce specs that tell what this happy zone, I'll call it, otherwise known as typical operating ranges. They publish this info for you. Now, it's not to say that you couldn't operate a tube outside of these given parameters. They're just telling you if you operate it within these parameters, they know the tube will operate well because that's how they designed the tube. Having said that, the tube manufacturers actually publish spec sheets, and this one was found in the RCA receiving tube manual. And what it does is it starts to tell you all about this tube. First thing it tells you is, hey, it's an 807 type tube. It is a beam power tube, and it is useful at frequencies up to 125 megacycles. I found that statement very interesting, and let me tell you why. If you think about 125 megacycles, we know that today is 125 megahertz. That's even further out than the top end of your FM broadcast band. So that typically goes from 88 megahertz up to 108 or so megahertz. You know, this thing could amplify and the entire FM spectrum from an RF standpoint. So this thing kind of goes from way down at 0 hertz all the way up through the audio range into the RF range and keeps going. So what you got to be careful when you're designing an amplifier that has a tube that can cover that broad of range is that you don't end up with either harmonics or parasitics, oscillations going on inside the amplifier that ultimately end up chewing up all your power, producing something that you can't even hear with your ears. So it's just a design consideration we have to be careful of when designing an amplifier that has such a broad, or designing around a tube with such a broad spectrum range. Okay, there's some useful information here in these tube data sheets. And by the way, if you're ever looking for a tube data sheet, just find them the way I find them. Go to Google, type in 807 data sheet, boom, up pops a couple different versions of it by different manufacturers. They're pretty much generally aligned with each other, but there's some useful information here for the average builder, I would say. Somebody that wants to do like we're doing in this video, finds a good schematic, wants to build it, maybe then they want to tweak it and perfect it a little bit. And then there's a lot of information in the spec sheets that the average builder, it might go beyond them. In other words, unless you were doing circuit analysis and design at a mathematical level and selecting capacitor values based upon some mathematical formula that you go through that ultimately helps you get there, you may not need all this information. And I'm trying to keep this video series focused on the average builder. Maybe later I'll do something at a more in-depth level, but the problem with that is the average viewer out there probably couldn't consume a lot of that without a heavy math and or physics background. So let's go ahead and dive in. The first one here is it tells us that the heater voltage, otherwise known as the filaments on this tube, is 6.3 volts plus or minus a little bit here. And it tells you it doesn't care whether it's AC or DC volts. And it tells you that each tube, when the heaters are lit up, will pull 0.9 amps of current. So that's useful information in doing a design. Let's say we're designing a stereo amplifier like we're going to do, and you're going to have two 807 tubes in this thing. Well, you're going to need to feed it with 6.3 volts of heater voltage at 0.9 times 2 equals 1.8 amps of current to ultimately feed the heaters because you've got two of them. Now, I will tell you that there's something called these kind of engineering design guidelines that a lot of people go by, and this is, there again, very subjective. But I'll give you an example. If you were designing an elevator and that was your job, and you knew that the most amount of people you could fit in an elevator was about 15, and the average person that fit in there might weigh about 200 pounds at the most, so 200 times 15, wow, you might end up with about 3,000 pounds that this elevator needs to lift up or down. So would you go build and design an elevator that could move exactly 3,000 pounds? Well, what happens if you happen to cram 16 people in it, or the average person in it happens to weigh 210 pounds? You certainly don't want this elevator to fail and fall and drop people, right? So people typically, when doing engineering work, over design. In other words, you don't want to get right there and operate at the maximum all the time. So instead of 0.9 times 2, 1.8 amps of current, you might want to pick a transformer to feed your filaments here that provided more like 2.2 or 2.5 amps of current, just so this thing's not constantly struggling at the absolute max at 1.8 all the time. Now, there is a spectrum of one end to the other of what you see people doing around design specs like that. Some people will say, well, wow, you will spend a lot of money buying 2.5 amp transformer versus you could buy a 2 amp transformer here, right? Well, the problem with a 2 amp transformer, maybe it works great, maybe it works fine, but maybe the design specs on it also say plus or minus 10%. Well, if it's a minus 10% and a 2 amp transformer would only be a 1.8 amp transformer. It means you're operating that thing at its absolute max all the time. Wouldn't want to go there. I'd recommend going a little further than that. You know, if you were designing an elevator, you'd probably design that thing for 2 or 3 or 4 or maybe even 5x. So this thing could carry 15,000 pounds, even though the most it would ever fit in it would be 3,000 pounds, just because you don't want it to ever fail or even get close to being near its maximum operating range. So I preach this a little bit right now because it plays out throughout the whole design of this amplifier. Me, if I was picking this, I'd probably go with something around the 2.2 range. That way, if it was plus or minus a little bit, I still have a little bit of what I'll call headroom. In other words, capacity to spare. Okay, some of these next specs won't mean as much to us, but and they would if we were actually doing deep circuit analysis and design. This 6,000 micromhos is basically, if you notice, micromhos, M-H-O-S, is kind of the opposite of ohms. Instead of restricting, it's actually how much this thing kind of actually helps amplify. So this figure here is a kind of a gain figure. The kind of the mu factor, we won't use that either. And the same with these inner electrode capacitances. Like I say, if we were doing deep circuit design and analysis, we would get into Miller capacitance and some other things. But we won't need that for the level we're doing because we're actually picking a chosen design and actually going to build it. But some of this here is kind of important to us. We get into a little bit of the position. You can either mount these standing up vertically or laying down horizontally. I will tell you, even though it says any here, I have read some things over time that say that the 807 doesn't work as well in the audio range laying down on its side. Apparently there's some sag in some of the physical components, and seems to work fine at RF, but not so great in the audio range. Talks about, you know, the diameter, the height, the weight, etc. But more than anything, we get down here into something we do care about, which is kind of the pin out. So this is if you're looking at the bottom of the tube and you've held this thing up. You'll notice here it says pins 1 and pins 5 are the heater. So that's if you were connecting up a transformer, an AC transformer, to feed the filaments here, you would get something with 6.3 volts, at least maybe 2.2 amps of current, and you would hook it up to pin 1 and pin 5, and it would light this tube up. If you'll notice here, pin number 3 is actually grid number 1 right here, which is what I typically call the grid. Back in the old days, they would have multiple grids, grid 1, grid 2, grid 3, etc. As time evolved, they started giving them different names. So grid 1 is typically known as the grid. Then you get into grid number 2 here, okay, which is the second grid right here, which is typically called a screen. And then you get into grid number 4 here in this one, which actually, by the way, it gets tied back down to the cathode. But grid 4 is also called the suppressor grid. And then the last piece here, which isn't on a pin, it's on the cap. If you'll notice back, I'll show you here, the tube unit, the 807 tubes actually have a plate cap on top of them, and that's where you pull the plate from. Hang on and I'll show you that real quick. If you'll remember, right up here we have plate caps. In other words, we're going to have to connect not only to the pins on the bottom of the tube, but we'll have to run a wire up and use a little device here called a plate cap connector, and we'll actually have to connect to the top parts of these tubes. You might wonder why you would do that. Well, certain tubes are designed to run at higher voltages, and when you got a lot of pins down here on the bottom and you're putting high voltage in between them, they get too close and they start arcing over. So tubes that are designed to operate at a much higher voltage, you'll start to see the plates break out and be separate from the bottom of the tube, or you'll see the tube get physically bigger so that the base is much bigger around and you don't have that closeness between the pins, not just on the outside here, but as they start to come together on the inside of the tube right here. Okay, the other thing that these data sheets give you are typical operating parameters, and it kind of breaks it down by section. If you'll notice here, it's talking about using an 807 tube as an AF, audio frequency power amplifier, and or a modulator like we talked about earlier, in a class AB1. Well, AB1 is a form of a push-pull amplifier, and it gives you all the specs and how you should typically operate it. Well, then it kind of goes into, say, in class AB1, let's see, AB2, then it kind of goes into class B operation, then it gets into class C operation, class C. It never covers class A in the RCA manual. Not sure why, but it doesn't. So ultimately, I ended up finding another spec sheet from a company called Brymar. They make 807 tubes as well, and they covered the specs on theirs for a single-ended or Class A amplifier, as you can see here. And I thought it was kind of interesting. It tells some of the similar specs: 6.3 heater volts, 0.9 amps, same specs we saw on the RCA amplifier. I thought this starts to get interesting, and notice these are all absolute maximum values. This thing operates at 600 volts anode voltage. Anode is the plate. Those two words are can be used interchangeably. And, if you're operating this thing at 600 volts, you're pushing it. But here, this is an interesting one. Anode dissipation, otherwise known as plate dissipation, and it's measured in watts. And a lot of people will pick up a tube manual, they'll scan through, and they'll say, hey, the 807 tube, it can put out 25 watts of power. Well, that's not necessarily true. And I got into a debate with someone on a Facebook group here recently. Ultimately, I ended up just walking away because I knew I was arguing a point that both of us thought we were right, and there was really no way to resolve it. So, but here's the way this goes. When it says plate dissipation, that is not the power output of that tube. What that figure means is it is the maximum amount of power that the plate, the physical plate inside of that tube, can dissipate. In other words, heat that thing can dissipate or handle without destructing itself. And that's 25 watts. Well, it's just like that elevator scenario. You would never operate this tube at that spec. And by the way, if you did, there would probably be a lot of distortion going on. So this is not a 25 watt tube. It's something less than that, and we'll see that here in just a few minutes. But don't let a lot of people pick this up. They'll say, hey, my amplifier, it's got two tubes in it. It's a 50 watt amplifier, because right here it says 25 watts each. And you got to realize that's plate dissipation, not actually power output. It tells you the screen too. Otherwise, notice here they actually call grid 2 screen, like I mentioned earlier. It should operate at around 300 volts. So plate at 600 volts, grid screen, grid 2 or screen at 300 volts. And it tells you that the screen can handle about 3.5 watts of power, absolute maximum. Okay, and if we scroll down here a little bit, we'll find the typical operating characteristics for a Class A amplifier. And these are minimum. This column here is minimum. This column here is maximum. So anode voltage would typically operate somewhere between 300 and 500 volts. And I think this amplifier we're designing is going to be around 400-ish or so. It tells you how much current that would pull. So, hey, if your plate voltage is 400 volts, and it can pull anywhere from 83 to 50. You could do kind of halfway in between there. So it's about, I don't know, 65 or so, 67 milliamps. Well, then that helps you pick the transformer. You go look at the plate specs. It puts out 400 volts, maybe with a center tap. And then you got to figure in how much current it could handle. You'd probably want to buy something for this amplifier that could either do 75 or maybe even 100 milliamps of current to feed the plate. So you've got a little bit of overhead and you're not running that transformer hot all the time. Tells you your screen voltage somewhere between 200 250 volts. Tells you your current that's going to pull. Tells you that your control grid number 1, is actually going to operate at a negative voltage. So we got to figure, as we go to bias this amplifier, we got to figure out how we're going to come up with this negative voltage. And there's a couple different ways of doing that. But this thing's going to operate between -12 and -14.5 volts. Wow, it comes right out and tells you that you're going to use a cathode bias resistor somewhere between the value of 140 and 280 ohms. And I can tell you this amplifier we're designing has a 190 ohm cathode bias resistor. It tells you that the plate impedance is somewhere between 2400 and 3900 ohms. Tells you that this thing, kind of its mutual conductance value, which we're not going to need to use. But this is a very important one right here. The optimal load. So in other words, when you go to buy the output transformer for your single-ended amplifier is going to be somewhere between 3,000 ohms and 6,000 ohms. Well, I can tell you the one we're about to build uses a 5,000 ohm impedance output transformer. In other words, you need a transformer that can go from 5,000 ohms on one side on the primaries to 8 ohms or 16 ohms or 4 ohms or whatever, maybe all those on multiple taps on the secondary. Here we go. Woohoo! Finally, it tells you between these design specs. In other words, if you're running this thing with all these specs on the right, this thing will put out 11.5 watts. If you're running this thing with all the specs on the left, in other words, a little cooler, not completely wide open all the time, this thing will put out 6.4. My guess is the design we're doing operating around 400 or so volts right down here in the middle. We're going to be operating around 8 or 9 volts, which is just perfect. You're not overheating, overtaxing, overdriving this tube constantly, etc. And it'll tell you that this thing will operate somewhere between 6 and 12%. Well, I can tell you we're going to design this thing much better than that, and we're going to get it way down below this 6 to 12% harmonic distortion. We're going to get it way below 1% is what we're going to do. And we do that by tweaking and optimizing the design. And then this thing goes on to show other things. It also starts to show plate curves and conductance curves, etc. And I'm going to stay out of all that for this video series, but hopefully you'll learn a little something here on what these values mean and why they're important. Okay, here we are with the final beginning design that I started with. There's this guy over in the Netherlands that has a website. You can just type in Triodic Amplifier. And this guy has got quite a few designs that he's put together. But one of them was this 807 design. And part of why I picked it was I really liked the design. Two, there's a lot of, seems to be good information out on the forums about it. And there's a good bit of discussion, so people knowledgeable about this out on the forums. And, I thought it was a, pretty neat design, and it worked well with the 807 tube here ultimately at the end of the day. And it looked like all the components were fairly easily obtainable. So at the end of the day, this is the design we started as our basis. And, so hats off. I'd like to thank this guy for his original design. But there's not a lot to this design, and we'll get into it here further as we walk through it. That's, groundbreaking. I mean, a lot of it's pretty basic stuff, but he does stitch together a few different elements and components coming from a few different designs I've seen over time that make this, at the end of the day, a pretty darn cool design. Okay, this is the schematic for the amplifier section of this Triodic design. And keep in mind, since this is the amplifier section, if you're building a stereo amplifier, you're going to have to build this whole piece right here twice. In other words, once for the left channel and once for the right channel in this amplifier. So let's do a little left to right walkthrough. I like to think of a schematic much like reading a book. You kind of read it left to right, and that's kind of the way I like to design schematics, and it's the same way this guy designed it. But over here on the left-hand side, what he's basically got is a couple different input jacks on the back of the amplifier, and then he's using some type of either toggle or rotary switch to let you select between those. Maybe that's your CD input, maybe that's your iPhone input, maybe that's some other input. It wouldn't be a phono input because there's no phono stage inside this amplifier. But you know, it could be a CD player, one of them could be your MP3 player, maybe something from your TV, etc. But I'm probably going to avoid all that and just have a single input on my amplifier. So I'll feed straight in and come right here. And this whole line on the bottom right here that goes straight across right here, if you notice it's tagged down right here, it is ground. So basically this is your ground bus or the chassis within the amplifier itself. So think about it. I'm just going to feed in, have a single input in here, and then I'm going to get to this place right here. And this is a potentiometer. And what does this potentiometer do? Ultimately, it is a voltage divider. So if you turn the potentiometer all the way to the left, basically what you're doing is you're sending more of your signal here straight to ground. So you're just throwing your electrons away right into the ground chassis of the amplifier, and less of it is making it over here to the grid of the tube to be amplified. If you turn the wiper to the right on this thing, then it would slide the other direction. You would be sending less to ground and more of it straight into this tube right here to be amplified. So that ultimately, turn it to the left, volume is quieter. Turn it to the right, you're amplifying more of your signal that you're sending to it. So volume is louder. So it's a volume control. That's all that is. You know, I'm a firm believer, it's kind of like I mentioned earlier, eating an elephant. But if you break down each piece of this thing one at a time, it's not so scary. You know, to somebody new to schematics and tube amplifiers, you may look at this thing and go, there's a lot here to that. Well, not if you break it down piece by piece. So you come out of this volume control, we'll call it, and you come over here and you're feeding into the grid of this next tube. And this, if you'll notice right here, it tells you it is half of a 6SN7. 6SN7 is a tube type that is called a dual triode. In other words, inside of one tube, there are two completely separate tubes inside of it. So you could look at it as being, you know, one 6SN7 and another 6SN7, but since they fit inside of one envelope, they kind of call it half of a 6SN7. And feeding in between this potentiometer and this grid is something here typically called a grid stopper resistor. These things typically 1K is a pretty typical value you see on those. They are designed to kind of reduce parasitic oscillations parasitics going into the next phase of the amplifier. So it's a pretty common thing to see these days. You'll notice here there's a resistor coming off the cathode of this thing. This is your cathode bias resistor. In other words, you're floating that cathode above ground a certain amount of DC. And ultimately that is determining the bias of this tube stage, and it also determines how much current at the end of the day actually flows through this tube. So this is one of the primary devices being used to bias this stage of the amplifier. You also have here on the plate a resistor, and that's kind of known as a plate resistor. It creates a load. And if your power supply feeds into here, you'll have some voltage drop across that, but not a lot. And ultimately, you'll feed the plate of this tube. So the way this works is signal comes in here, goes to the grid. The B plus on this thing has a much bigger swing than the grid does, and you're basically varying the flow of electrons through this tube, which ultimately varies the swing here on the plate of this tube. So if you take your output off the plate, which we're doing right here, what you actually get is a much amplified signal compared to what was fed into this thing. At this point, you feed over into what I call a decoupling capacitor. The world calls them coupling capacitors, and it's what they are. You're coupling one stage to the next with a capacitor. I like to call them decoupling capacitors because that's kind of what you're doing. You're decoupling this stage here from this stage here. and making sure that the 300 volts sitting on the plate of this tube doesn't come straight across and end up on the grid of this tube. If you did, this tube would, on the inside, would start glowing red, much like a Christmas tree, and it would burn up very, very quickly. So you got to keep the DC from this stage off of this stage right here. And you do that being a coupling capacitor. Remember, capacitors pass AC signals freely, and they block DC. Okay, up next here, you kind of feed into another grid stop resistor here, and it's also, you've got to be able to bias this grid relative to ground, and that's what this 220k ohm does right there. It basically provides the voltage lift on this thing. And similarly to the other tube, you've got another cathode bias resistor here feeding down, and this circuit right here is an interesting one. It's a so I kind of lied when I said this was a single-ended amplifier. I threw a trick in here by choosing this triode Dick design. This second phase right here, if you'll notice, this is he's using a whole 6S7. In other words, 2 halves of a 6S7 here. So ultimately, you'll have to have 1, 2, 3 physical tubes in each side of this amplifier. And what this is this is called an SRPP circuit design right here, and I think that stands for shunt regulated push-pull phase. And what it actually is right here within this design. This is actually, you could kind of think of it as like a push-pull configuration with a built-in phase inverter. And I know we didn't talk a lot about phase inverters earlier, but basically the interaction between the plate of this tube and the cathode of this tube, between this 1K resistor right here, and the feeding of this up into the grid coming from this plate, ultimately kind of creates its own little phase inverter. In other words, these two tubes interact with each other heavily, but the bottom line is you're kind of feeding off of this plate of this into the grid of this, ultimately taking the output of that through another coupling capacitor. And if you'll notice, you fed this B plus over here with a slightly higher voltage than you did this previous tube over here. And once you get into this next stage over here, there again, another resistor to kind of lift this grid off the ground, and you know, another grid stopper resistor feeding this thing in. If you'll notice, we're now feeding into a pentode. A couple of these tube pins get tied together. So the cathode as well as this suppressor screen up here get tied together, and we're going to feed into the grid. Don't let that confuse you. There's no dot right there. That those three are not all tied together. The grid here is separate from the cathode and the suppressor screen up here. So you're feeding into this, and ultimately you're coming out of this into the output transformer. There again, you've got a cathode bias resistor, and you've also got a cathode bias coupling capacitor, or cathode bias capacitor right here. And then finally, you're feeding out of this thing, feeding out into the transformer itself, which ultimately feeds the other side of the transformer, the speaker. A few more pieces here. You've got to give about 250 volts to the screen of this thing. So this thing takes a little bit off the B plus and brings it around, drops it through a dropping resistor. And then ultimately it's using a couple Zeners stacked in series with each other as a crude form of a voltage rectifier. So you can, like in the case, the one I'm going to build, I think I've got 75, 75, which gives you 150, and then 100 volt 1 watt Zeners. Ultimately, it'll hold this level right here at 250 volts, because this screen grid right here, it's very important that the voltage on it stays consistent. So we're doing a little bit of regulation around that, and this this capacitor right here helps regulate that as well. So then you got your music playing out your speaker. You're also taking a little bit off of the transformer tap here, typically at the anode tap, and you're bringing it around, and it didn't show this, but it brings it all the way back around here through an 82 ohm resistor. In other words, drops the output just a little bit, and it brings it back here and ties it into the cathode of this first stage, and that is what is known as global feedback. In other words, you're taking feedback from one portion of the amplifier, and you're feeding it back to another portion of the amplifier. And what that does is it takes a little bit of a sample of the output, feeds it back to the input, and the whole course of doing that, and you feed it back into a place. If you fed it back right here into this input, then it wouldn't be a negative feedback, it would be positive. You're feeding it to kind of compensate here where this cathode is out of phase with this grid right here. So in other words, at the end of the day, it's helping correct any anomalies in this circuit. Ultimately, feedback does a couple things. One, it kind of reduces the overall bandwidth of the design, which can be seen as a negative, but not necessarily bad as long as you got enough bandwidth on each side. But what it does do is it helps reduce distortion in an amplifier, and it makes this amplifier much more tolerant to what would be considered power supply hum, noise, etc., anything affecting this overall circuit. And you notice it's called global feedback. If you're ever taking feedback of an amplifier and feeding it back in, like right here locally, that would be called local feedback. But you get more efficiency, I would say, out of feeding back here into the front end and feeding it all the way back through. It kind of helps course correct all the way through on this amplifier. And you can see here, I've kind of picked this Ed Core transformer that I'm going to be using for this thing, and I've got those on order. They have not shown up yet at this point in time. So hopefully you can follow what I talked you through here right now. A little bit of this probably a little fuzzy for you, I would imagine. If so, there's a couple good articles out there on SRPP. Just go type in Google, type in SRPP circuit, and some good reading out there. But I think this SRPP right here is something very unique to this design that Dick put together. I also think this using some global feedback and a single-ended amplifier was a pretty unique element. And I also think this using of these Zeners right here to regulate this this screen grid was a little bit unique. So he took a traditional classic design, put a few tweaks on it here, and made it something of his own. And I actually kind of like the design. I've worked with a good bit of single-ended designs in my time, and this one's kind of caught my attention as something I like. Okay, this power supply, unlike the amplifier piece of the schematic, you only need one of these. It's designed to feed both sides of a stereo amplifier. And it's a pretty simplistic design here. If you look here on the front end, you've got a 120 volt transformer. Got some a little bit of noise capacitors on the front end here, or on the switch, to help keep the switch from arcing, and to basically help with noise on the front end here. And they've got a 2 amp fuse on this thing, and then ultimately they're feeding into a transformer here. And I've been looking at different transformers to use for this thing, and there's quite a few that would ultimately end up working. But here's the basic specs you're going to need for one of these things. You're going to need something that can feed 5 amps 5 volts, because this tube it's using is either a 5R4 or 5U4. It's going to need that, and it's going to need 3 amps of it. And they also, for this design specifically, because of the SRPP piece of this, it needs a center tap right here, and we'll talk about that more here in a little bit. It's also going to need a 380 volt at a minimum. You could probably use upwards of 400 volts. You could probably use downwards of 350 volts if you happen to have a transformer laying around. But you're going to need at least about 300 milliamps total to power this thing. And you'll need a center tap. In other words, this thing is 380 volts positive, 380 volts negative, with a center tap here in the middle. You're going to need a transformer that has 2 amps at 6 volts, 6.5 volts. We talked about that earlier. And so there again, they've got a version here that has a center tap, and I can show you why that is here as we talk about this circuit here for the SRPP. And then you're going to need, for the other part of the 6S and 7s, another 6.5 volt circuit, and another 6.5 volt here to feed the at 4 amps. Now, if you had a transformer that had, let's say, 6.5 volts center tapped at 10 amps, You could feed all of these with the exception of the 5 amp circuit over here. Matter of fact, there's even some trickery you can do with circuits to take what would be 6 volts here and do a little bit of drop down to feed the 5 volts you would need over here for this. But each of these sections here are basically designed to feed your filaments and or heater voltages. This one up here designed to feed your filaments of this rectifier. And then ultimately this is where you feed your main power going into your high voltage B plus going into the rectifier here. Hope that makes sense so far. Okay, if I've lost you at any point, don't worry. Go back and rewatch again to see if you can pick it up the second time around. If not, hang in there. The purpose of this video is to bring a schematic to life. And what I'm going to end up doing as we get into actually building this thing is I'll be able to hook an oscilloscope up and or voltmeters and show you various voltages and what's actually going on relative back to the schematic. So my goal is to not only just walk you through what these components are, but then when we build it, actually let's go measure these things and see what we've actually got and what's taking place in these circuits. So hopefully that'll reinforce the learning here and really bring it to life by actually seeing it being built. But you know, a good example of where, you know, sometimes it's hard to just comprehend something, but when you actually see it play out in the real world, one good example of that is this stage right here is a rectifier stage, and what you're basically doing is this filament voltage right here coming over here and feeding the cathode of this tube. And what it's doing is it's lighting up the heater. Well, this is a directly heated tube, so at the same time it's kind of heating up the tube, it's also playing a part of the rectification. In other words, at the end of the day, you're feeding 5 volts into this thing. It's also picking up the rectified signal coming between these two halves of the input here coming out. You've probably got about 600 volts sitting right here coming off of this thing. So not only do you have a 5 volt AC signal, but you got a 600 volt DC signal all operating on these same wires, and you'll see how that kind of plays out when we build this thing. But ultimately this thing comes over here and you probably, like I say, probably got somewhere in the 600 volt range sitting here right now. This first capacitor right here, think of it as a reservoir. You're filling it up with 600 volts, and as this amp pulls away current that it needs, that capacitor kind of kicks in and says, here, let me help fill in the gaps. And so it starts to smooth out the rectification that took place back here in this stage. If you want to see more on rectification, it might be worth you going and just Googling a little bit on it. It's really easy to find information on what a rectifier does. But then at that point, you're basically using what is known as a CLC filter. In other words, capacitor, inductor, L is the abbreviation for inductor, and then another capacitor. So, and then it also splits it apart right here. So in other words, here is a capacitor and an inductor and another capacitor here for the left channel. Here's your capacitor, an inductor, another capacitor for the right channel. In other words, you're starting to, this is what's called a split rail power supply. You've taken your DC voltage and you're starting to split it out. And the reason you do that is you don't want the demands placed over here by the amplifier on this rail to interact with this rail. In other words, if a heavy bass note hit on the left channel of the amplifier while the right note was playing some a higher treble note or something, you wouldn't want this bass note swamping or affecting your treble note over here on this other channel. So that's the reason you do this split rail. So you basically bring in an inductor, which and keep in mind what inductor's purpose is they violently fight for a change in current, and whereas these fight a change in voltage. So they try to maintain a constant current going out to the supply. And then the second capacitor here is doing the same thing this first one did, just another level of kind of capacity on demand. Think of it as a battery ready there to serve whenever this circuit gets swamped. And then these resistors right here, here's what they do. So at this point, we're sitting at 450 volts on the left, 450 volts on the right. Keep in mind, these inductors have some resistance built into them. They drop down just a little bit. And then you're intentionally at this point dropping down again. In other words, these values get chosen based on the voltage that you're measuring right here to get you to the right voltage you want at this B plus place. Remember earlier, B plus 450 volts. Remember right here, we need 450 volts in our circuit to feed this B plus. Right here, B plus plus 350 volts. Well, remember, we wanted to feed these tubes with 350 volts. So we're using the same power supply to feed all these tubes, but we need different voltages because of the design of each phase and or the type of tube being used. So if we come back over here, then there's the B plus plus plus, which is 300 volts. And if you come back over here, we need 300 volts to feed this tube right here. So that's what that ultimately ends up doing. And these other 22 microfarad and 10 microfarad sections are ultimately designed to keep, when this section here pulls down a heavy current load, keep it from affecting this section. When this section pulls a heavy current load, keep it from affecting this section. That's what each of these capacitors right here do. They have demand on reserve, ready to hand off, capacity of power waiting to go, and that's what they do. Ultimately then down here, this little trickery circuit right here, what it does is it basically floats this 3.5 volts off of ground. Off of ground a little bit. So in other words, what it's doing is you're pulling off of your main power supply rail, doing a voltage divider here, and you're floating this voltage above ground. And that's because SRPP circuits seem to operate better with their filament voltage being floated above ground. It has some to do with the way this whole circuit interacts with each other. And then ultimately there's a little bypass capacitor on this thing right here to give you a little bit of regulation on that floating voltage right there. So all in all, it's not that complicated of a circuit. It's telling you that all these capacitors right here need to be at least 630 volts. They used MKPs in his, and I'm actually going to try that. I've never built a single-ended amplifier, or any amplifier, matter of fact, by using basically polypropylene MKP capacitors in the power supply. I've always used electrolytic, so I thought I'd try something new here. Should be fun. Hopefully you've followed along a little bit. If you need me to come back and explain a section better, give me some feedback. Tell me what you need to know better. And when we get to the actual build and I start referencing back to these schematics, I can do so. Okay. I ran out of time, and we're going to have to make the components and the building materials into the next video. I was wrong and under anticipated either how much I rambled or how in depth I went, or just how long it was going to take to do the design aspect of this. So stay tuned, part 3. Probably won't get to it today, maybe next weekend or one night this week, but we'll get into the components and building materials. Then hopefully by next Sunday we can actually be building this thing over here on the bench live and showing you that as we go. Thanks for watching, everybody. Stay tuned for part 3. Give me some thoughts on this series.